My name is Praveen J. Kumar, and today I'll be talking about AI and brain-machine interfaces. In this presentation, I'll introduce concepts of both brain-machine interfaces and AI, or artificial intelligence. Then I'll show how to combine those technologies and step through the process of doing so. And then lastly, I'll show some applications by showing some examples of the technology. So what are brain, computer, or machine interfaces? There's two major types. The first reads signals from the brain, and there's three primary ways it's done. The first is using EEG data, in which electrodes can be placed on the outside or the inside of the scalp. Those on the inside of the scalp produce much better signals but require surgery to be placed. The second way is using an fMRI machine or an MEG machine to measure brain signals. Both are very large and expensive and will probably not be used for small portable brain-machine interfaces. The last major technique is using near-infrared spectroscopy by shining an infrared light onto the skull. Of these three, the most popular method that's currently being used in brain-machine interfaces is using electrodes to get EEG data. The EEG data is then taken in and processed, so it could be used to power something such as a piece of machinery with just one's thoughts. In one study, monkeys initially controlled a robotic arm using a joystick while their neural activity was recorded. Using that data, electrodes were placed on the monkeys, and the monkeys were still able to control that arm with just their thoughts. The second type of brain-machine interface is when you send signals to the brain. So you process some sort of data and convert it to a voltage to be applied to the neurons, hopefully triggering the right action potentials. This could be used by finding the neural response from a seeing person's brain from a certain stimuli, such as seeing the color green, and then using a camera on a blind person to capture that stimuli and respond to it in the same way. A more difficult example is to give control of an arm back to someone who doesn't have any control. A system must learn of the signals that are produced from the brain associated with the different actions such as closing your hand, opening your hand, making a fist, before it can be implemented, which then goes into AI, or artificial intelligence. So what is artificial intelligence, or AI? AI is the simulation of human intelligence processes by machines, especially computer systems. These processes include learning, the acquisition of information and rules for using the information, reasoning, using the rules to reach approximate or definite conclusions, and self-correction, as defined by TechTarget. AI essentially is able to use the massive amounts of data that we're able to collect, and much like a human is able to process that data and give some output or give some action based on that by modeling the data and making a prediction. AI is a massive field with many different sections. One of those subsets is machine learning. And in this presentation, I'll be focusing on the application of machine learning and AI in brain-machine interfaces. So why do we need both? Well, to put it simply, brains are some of the most complex things in the world, as we've probably learned through the course of this class. And as there are billions of neurons working together to help us do everyday actions, such as me presenting to you right now, it's hard to capture all of the activity with just a human. So AI and machine learning allows us to learn about those neurons and the interactions of them and the action potentials that are occurring at a much faster rate. This allows us to, instead of waiting through multiple studies and multiple trials of attempting to find which neurons are associated with what action, we're able to use AI and machine learning to quickly find those and able to progress much faster in the field. Another aspect is being able to combine a human intelligence with artificial intelligence opens a huge amount of doors. Many companies are trying to work on this so that we can augment our brains and our intelligence so that we're able to reach new potentials that we could never have imagined. First, we have to observe which neurons are associated with our action of interest. For example, if we want to control a prosthetic arm and we want to try to close the fist, we would maybe not only have to consider neurons in the motor cortex, as one may presume. Additionally, we do not know now if those neurons remain constant across different people, which introduces new complications. So in order to model those neurons, one of the most common ways to do that is using AI or machine learning. Machine learning helps modeling the neurons that we need, testing that model, and iterating until that model is the best it can be, and we've specifically identified the neurons that we need to. One common method being used to identify neurons is linear classification. Linear classification bounds regions based on a set of characteristics. In the image, you can see that airplanes, cars, and deers images are classified by the lines such that on one side of the line it fits a certain classification and something else on the other. The same can be done with sets of neurons to identify which send an action potential to perform a task, or multiple sections of neurons could be classified into different actions. Furthermore, simply doing this across the brain is complex and result in incorrect results. So the first steps in feature selection must be done before attempting to model the neurons. There is some pre-processing involved that requires the humans involved in the modeling to identify certain parts of the brain or certain neurons to target before letting the model take its course. Once the proper features have been identified, we can then get the appropriate data from the interaction of the neurons. The signals that we get will be very small and susceptible to interference, so they may need to be run through a filter and an amplifier. Once we have that final output from the neuron, we must translate that into an action. So if the action is to close our hand into a fist, a voltage have to be applied to the proper motors of the prosthetic arm that would allow the fist to close, as seen in the GIF or GIF. The last two steps are then repeated and iterated until all the desired actions in the prosthetic arm have been properly associated with the neurons and their action potentials. The final step is just putting it all together, ensuring there is no loss of functionality after the whole prosthetic is working together with the neurons. Now I'll show you different applications of the technology. I'll start out with a video about BrainGate.
Matthew Nagel was paralyzed from the neck down after being stabbed several years ago, but technology gave him hope. He was one of 4 testing BrainGate, a new technology where a chip is implanted in the brain that picks up electrical impulses. A computer then interprets those impulses as actions. The chip is implanted just beneath the patient's skull and is only a few millimeters square. Here's Matthew playing a computer game. He's not using a mouse or a joystick, rather he's thinking of where to move the paddle. All thoughts are electrical impulses, and after extensive research and testing, a computer has been trained to decode those impulses and create the corresponding actions.
Now close it.
Now close. Eyes open. That there, not there at all.
This is Matthew completing another task where he's controlling the green dot with his thoughts and trying to follow the red dot. At Boston's Museum of Science, BrainGate's creator talked about the technology and what he hopes it can do.
So in 5 years, what we want is individuals who have spinal cord injury able to feed themselves, to move their limb to their face, potentially stand up, things like that. That 5 years would be ambitious, but potentially that would be beginning to happen. In 50 years, it's very hard to tell, but I think we'll have people with much better, allowing people much better control, that they would be able to carry out a range of normal functions, but maybe not even to the level of, say, typing with their fingers. But again, we don't know.
Donahue went on to say that many tens of millions of dollars have been spent so far by his team to develop BrainGate, but the technology is still in its infancy. Once on the market, he expects BrainGate to cost tens of thousands of dollars for each patient, though he believes insurance will cover most of it. Donahue and his team are evaluating the data from the trials and looking to expand the program in late 2008 or early 2009. For the IDG News Service, I'm Nick Barber, reporting from Boston.
In the last video, we were able to see a couple different examples of what BrainGate is working on. Here is another example that happened in a hospital in the Netherlands. A paralyzed ALS patient was taken in and had electrodes surgically placed in her skull. Those electrodes were then connected to a transmitter as seen in the black in front of the patient's mouth in the clip. The signals from the electrode were amplified and then transmitted and converted to mouse movement along a keyboard. The patient was then able to move the mouse along the keyboard to produce words that the system would then speak out loud. Many others have researched using external caps of electrodes for a similar use to allow patients to talk. But the most unique aspect of this implementation is that the electrodes are invisible and implanted, and the technology can even be used at home. This application is similar to the example from before of a prosthetic that is powered by the brain. This one works a little bit differently, however. Usually, when a person is missing a limb and using a brain-machine interface, the brain sends out an error-related potential, or ERRP, which is effectively an error signal. So, for example, if we try to grasp a glass of water in front of us, the prosthesis would understand that it failed if it does, and the next time it'll change accordingly to try to get the desired result. The goal of the whole machine is that when all the actions are performed, there are no longer ERRP or error messages generated. Essentially, it's a trial and error system in which the robot attempts to perform an action and is corrected or rectified by the human user, who is able to communicate that through the interface. For example, one of the tasks that the participants had to do was point out an object across the room. The researchers found as the arm was able to respond to these different movements, it was able to build up a base of all the correct movements and build up a range of different movements from that basis. The last example I wanted to talk about is words of interest. This example differs from the previous two examples and some of the other topics I've talked about in this presentation so far, in the sense that the electrode data has not been mapped to an action yet. However, I found this research to be very interesting and very applicable in the sense that they're using machine learning with brain-machine interfaces. In the study, electrode caps were placed on participants. Those participants then read through Wikipedia articles. As they read through the article, different words stand out to different people. And through using machine learning, the scientists were able to identify which words stood out to which participant in the study. So, for example, if you were reading a Wikipedia article about action potentials and the word neuron stood out to you, the scientists would be able to identify that without you having any verbal or physical input, just using the electrodes on the brain-machine interface. While they haven't put this and implemented this into an action yet, there are a variety of different potential opportunities available with this information. One side is using marketing or advertising. Advertisers would be able to better target each individual person by seeing what they react to, what colors or what words or what things stand out to them, and allow them to change their advertisements based on that information. A more benevolent example may just be if you see some movie or projection on a screen, it could annotate it and change it as a response to your interests, which could then allow you to make more interesting notes or make more interesting content in general. Lastly, I just want to talk about the challenges in AI and brain-machine interfaces that are currently being faced to show what could come in the future. One of the major obstacles is feature selection or feature discovery. As I alluded to before, feature selection specific to brain-machine interfaces is selecting the specific neurons that are associated with each action that you are trying to emulate or simulate. So, when I'm lifting my arm, there may be neurons in my motor cortex and other parts of my brain that are all being fired to make sure that action occurs. This is difficult as there's billions of neurons working together to perform everyday tasks in all of our brains, and it is difficult to model all of that. Machine learning methods are being currently implemented to try to better model that and to identify those neurons. However, there is difficulty because there is a huge possible problem that the neurons activated when I lift my arm may not be the same as when the neurons activated when you lift your arm. That would mean scientists would then have to include that learning ability into their brain-machine interfaces when implemented into humans, which would then have to add a lot of computational complexity and possibly make the brain-machine interface bigger. The second obstacle is combining advancements in both fields. So AI and brain-machine interfaces are two of the most popular fields in the world right now. They're very fastly being innovated in and coming up with new methods and new methodologies, and new research is coming out all the time. Attempting to combine both of these is obviously difficult, but once we do, and once we're able to implement more AI methods into the brain-machine interfaces, I think the progress will be expedited. And lastly, augmenting human intelligence is not an easy task. In the picture, I've pictured Elon Musk, who started a company recently called Neuralink. Neuralink is attempting to have brain-machine interfaces that would be implanted in our brain that would help humans become essentially superhumans. It would use both human intelligence and artificial intelligence to allow us to process and think about things in new ways that we could never have seen before. This is a somewhat of a moonshot task, but many people are working on it, and I believe it will happen one day. Just to summarize, today I introduced the concepts of both brain-machine interfaces and artificial intelligence. Then I showed you the process of combining those technologies, some different examples of those technologies being implemented right now, and some current challenges that people working on the technology are facing. I hope you will be able to learn a lot from this presentation and will be interested in looking and working in this field in the future. Here are the sources that helped me make my presentation. Any questions?